Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to discuss about another application of dynamic programming, which is nothing but all-page shortest path problem, which can be solved using Floyd's algorithm. Now here you can see what is this problem first. You are given a directed connected weight graph. For each h, u comma e, b belongs to e, a weight is assigned. Okay, for every h, a weight is assigned. Now, all-page shortest path problem is to find the shortest path from U to V for every pair of vertices in the given graph. So here you need to find the shortest paths between every pair of vertices. That is, here you can see an example graph is given which contains 4 vertices, 1, 2, 3, 4, and there are some edges are there between these 4 vertices, and each edge is assigned with a weight. Right. Now here your problem, all-page shortest path problem is to find the shortest path from 1 to 2, 1 to 3, and 1 to 4. In the same way, the shortest path from 2 to 1, 2 to 2, 2 to 3, 2 to 4. Right. In the same way, you need to find the shortest path from 3 to 1, 3 to 2, 3 to 4. In the same way, 4 to 1, 4 to 2, 4 to 3. Like that. For every pair of vertices, we need to find the shortest path. So from starting one is the initially, one is the source, and the destinations are 2, 3, 4. So what are the shortest paths from 1 to 2, 1 to 3, and 1 to 4? You need to find it. Next, 2 becomes the source, and the destinations becomes 1, 3, 4. Right. Next, 3 becomes the source. 1, 2, 4 becomes the destinations. Next, 4 becomes the source. 1, 2, 3 becomes the destination. Now I need to find the shortest paths between every pair of vertices in the given graph. That is to be called as all-page shortest path problem. Here you can see the example. The shortest path from node 1 to all other nodes are represented. So 1 to 2, the shortest path is directly edge which is present between 1 to 2, and 1 to 3, the shortest path is 1 to 2 and 2 to 3. So here 2 minus 5, the shortest path is minus 3 between these two, and the shortest path between 1 to 4 is 1 to 2, 2 to 3, and 3 to 4. It is nothing but 0 path we are reaching. Right. Since 2 plus 3 is 5, 5 minus 5 is 0. Right. Since negative weights are there. So sometimes there may not be present the negative weights. Right. Now coming to 3, the shortest path from 3. The shortest path from 3 to 1. 3 to 2, 3 to 4. Let us see. Shortest path from 3 to 1 are 3 to 4, 4 to 1. Right. Shortest path from 3 to 2 are 3 to 4, 4 to 1, and 1 to 2. Shortest path from 3 to 4 is this one. In the same way, shortest path from 2, that is 2 to 1, 2 to 3, 3 to 2 to 4. Now here 2 to 1 shortest path is 2 to 3, 3 to 4, 4 to 1. 2 to 3 shortest path is this itself. 2 to 4 shortest path is this one. Right. In the same way from 2 to 4. So here we are going to find the shortest paths from between every pair of vertices. Here this represents the shortest path from 1 to 2, 1 to 3, and 1 to 4. This represents the shortest path from 2 to 1, 2 to 3, 2 to 4. This represents the shortest path from 3 to 1, 3 to 2, 3 to 4. This represents the shortest path from 4 to 1, 4 to 2, 4 to 3. Like that, we are going to find the shortest path between all pairs of vertices. Right. I hope that you know the difference of edge and path. So here we are going to find the path, shortest path. Right. Now, how Floyd's algorithm can be used to find the shortest path? That we need to know. So Floyd-Wasser's algorithm is used to find the shortest path between all pairs of vertices. Now here, first we need to write the adjacency matrix. How the adjacency matrix is represented in case of all pairs shortest path problem is, we need to use cost adjacency matrix since each edge is assigned with some weight. So you know, I hope that you know the difference between adjacency matrix and cost adjacency matrix. In case of adjacency matrix, I have the entries only 0 and 1. If there is an edge, the entry becomes 1. If there is no edge, the entry becomes 0. Right, in case of adjacency matrix. But in case of cost adjacency matrix, it is different. three entries will be there. If there is no edge from I to j, then its value is represented with infinite. If there is an edge from I to j, then its value is represented with weight assigned to that edge. And if the two nodes are same, I to I, the cost of I to I, j to j can be represented as 0. The three entries are 0, wij, and infinite. Like that we can represent. So here you can see cost of I comma I is 0. Cost of I comma j is equal to weight assigned to the edge ij if it is present. If it is not present, then its value becomes infinite. Now here you can see the example as well. Here I have a graph, a directed graph with some edges, and each edge is assigned with some weight. Now totally 4 vertices are there. Those 4 vertices are A, B, C, D. Now let us see A to A, there is no edge. And since cost of I to I is 0, that is A to A is also becomes 0. Cost of B to B, cost of C to C, cost of D to D. These all to be represented as 0. And let us see, cost of A to B, there is an edge. I can write its value as 4. Cost of A to C, there is an edge. Its value is represented as 1. Now here you can see cost of C to B. C to B, there is no edge. So that's why its value is represented as infinite. In the same way, D to C. D to C is also there is no edge. So its value is represented as infinite. Right. So like that, first I need to find the cost matrix. So after finding the cost matrix, I need to find the shortest path matrix. So here this is the cost matrix. This is the shortest path matrix. Here you will not see that infinite here. Right. The infinite is replaced, but some other values are also replaced. Other values are also replaced, right? So you cannot see that the infinite here. The values are replaced, right? So this is the cost matrix. This is the shortest path matrix. The entries which are present in this shortest path matrix are represented here itself. So the shortest path from A to B is direct path. The shortest path from A to C is also a direct edge. But even though there is direct edge from A to B with cost 3, but the shortest path is A to C and C to D, which can be reached within the units 2. But here the direct weight is 3. So whether 3 is small or 2 is small, if 2 is small, the shortest path is A to C, C to D, not A to D. Right? In the same way, B to A, B to C, B to D. C to A, C to B, and C to B. D to A, D to B, and D to C. Like that, I go for finding all the shortest paths and their costs. Right. So here you can see the Warshall's algorithm, how it can be found. So this is the Floyd-Warshall's algorithm, which is used to find the all-page shortest path problem. Here cost 1 to n is the cost efficiency matrix. Here n is the number of vertices, and A is the shortest path matrix. That what I want to find. Now, what is the first step that I am doing is, first we need to copy the cost matrix into A, which is nothing but shortest path matrix. So here this is the cost matrix. So initially the entries which are present in the cost matrix are directly copied to A, right? Which is nothing but shortest path matrix. Later we can update those entries. Now, for the updation, here we are using this loop, right? Now, what I am doing here in this loop is Aij is equal to minimum of Aij comma Aik plus Akj. That is, I is a vertex and j is another vertex. If there is a path from I to j whose cost is, let us say, k. Now, here I have another vertex k. Here I have a path from this to this. This is having a cost of A. This is having a cost of B, let us say. Now, what I am finding here, minimum of these two values I am taking as I am updating. A contains the cost matrix, right? In this cost matrix, the entry Ij means A to A or A to B, A to C, like that. We need to consider different entries. Now, how this entry can be changed is, with the minimum value we are going to update, right? Now, let us see. Here, minimum of Aij. Initially, Aij is K, comma. What is Aik? A plus B, A plus B. So out of these two, which is minimum, that value is represented here, right? So in the above graph, here you can see that one value I show A to D, right? Here I am taking A of A to D is equal to, what is this one? Minimum of A of A to D, whose cost is 3, comma. Here I want to move Y as C, right? Here I am taking K as C, right? So A of A to C plus C to D, right? A to C. What is A to C? A to C is 1 plus C to D. What is C to D? C to D is 1. It is nothing but 2. So here directly A to D is 3. But when I am moving A to C, C to D, it becomes 2. So out of these two, which is minimum? 2 is minimum. So A to D value is updated as 2. That's what we will find for all the entries. How many entries are there here? Totally 16 entries are there. All these 16 entries will be updated using this formula. So, which gives the shortest path always, shortest path matrix for the given directed braid graph. So, I hope that you all understood the algorithm for this. Try to solve one more problem. Then you can clearly understood how the entries of shortest path will be changed. Thank you for listening. Thank you.